Hi, we're from the musical playground team. My name is Mehul Garg.
I'm Andre. I'm Kevin Chung.
So some background on our project. We're targeting pediatric stroke patients. A stroke occurs when blood flow is cut off to an area of the brain, leading to cell hypoxia. The cell doesn't receive enough oxygen, and if this happens for a long enough time, the cell dies. Some common effects of strokes include permanent or partial loss of speech, movement, or memory. You can see on the right, this patient has a blood clot near the brain, and depending on where this blood clot occurs in the brain, it can affect a different part of the body. For our project, we're targeting a blood clot that occurs in a part of the brain that controls your motor movements, or in the prefrontal cortex. So for some of these patients, especially for children, one thing that they go through is physical therapy to regain their muscle strength. And the goal of physical therapy is to develop their arm control and coordination and overcome their muscle spasticity. So we're trying to go against what has occurred in the brain and give some of that coordination to the muscles itself. So the goal of our project is to encourage patients to improve their limited arm motions through music. Music therapy has been shown to be successful in pediatric patients. It's both a motivational tool to keep them interested and continue going to the therapy, and is also a quantitative tool for both the family of the patient and for the therapist to measure their progress. Our project is focused towards people who experience lack of muscle movement and coordination in their arms due to a stroke. And the goal of our current goal is to design the task-oriented learning game by the end of this quarter at the Winter Design Review. This task-oriented game will analyze the user's movement and give feedback in real time, and we'll model it with a sinusoidal movement in the x-axis. So basic requirements of our project: we collected acceleration data from the therapist, which currently we're modeling as a sinusoid, and we established that as the baseline. Then the patient, we collect their acceleration data and compare the two curves to each other. And ideally, the patient is trying to model what the therapist has done. And we'll distort a song according to how well or poorly they've done based on their performance. And as they're moving, so this is real-time feedback, they will hear the distorted song. And Han's going to go into more of the technical aspects of this project.
So the technical work of this project is, we kind of split up in three subsections that you can see. There's mostly the research about the stroke therapy, and Mehul was kind of the lead in that. Another section was understanding correlation, pattern recognition. So this is just analyzing the data and comparing it to, as Mehul said, the baseline curve that we set, and I was more of the team lead for that. And our last is just to learn Java, because none of us really knew that coming into this project, and then how to access the different components like accelerometer and speakers through the phone, and Kevin was the lead in that. So design process, so we initially got this project from a summer student previous to us. The initial project originally was a small handheld device, which you'll see that later on. So what it initially did is it read hand motions as defined by a therapist or just a person initially, and from there you hand it to the person, another person, or you can do it yourself, and then you try to recreate those motions. Some problems with this is that it uses two Arduino boards. One was to play music through a wave shield, and the other one was to actually analyze and compile the data. As many of you know, that Arduino boards, they only hold about like 250 kilobytes of data, so that's not too much to mess around with. And you can, how the student previous to us overcame that is he split up the data into 4 subsections. So he had a beginning, 2 middle sections, and an ending section. And how he split it up was just however long it was recorded for, he split up the time into 4 different groups. And from there, he took the average acceleration between those 4 groups. And you can see how this is a problem, because you can be like having positive acceleration and switching down negative, but it would take out the average and read as a 0 acceleration, and that's not really what we wanted to encompass. And then another problem was just the shape of the project before. It was kind of a bulky cylinder, which might be hard to grasp if you have strokes or our target group, because it's just a big box. And as the last one is just the lack of resolution, and so it really only played 4 tones, or actually, 4 tones, and based on that 4 tones, 1 tone for each group, subsection group, And based on that, it was either like a high pitch tone or low pitch tone, and it was kind of hard to tell if you were doing well or not doing well at all. So that's kind of the main problems of the device. As you can see, this is the initial device. So this red button here is what you would press before to measure the motion, and then there's another black one, which is kind of hard to see here. This is kind of what you would press to recreate the motion. And then inside the box, you see there's two Arduino boards. That front one you see facing is the one that would record that would analyze the data, and then there's one on the back side of that holds the wave shield, which would play the tones I was talking to about. And then, so this is kind of the flow chart of that initial project we have, and our project is following a similar suit to that. So initially you start up here in the power state, and then as I said, that therapist would press that red button that you saw, and from there you would record a movement, and from there you hand it to the patient, and then, well, it actually would play a reference tone, but then you'd hand it to the patient to try to recreate the motion, and then from there it would tell you, it would play the tone back, and then it would play either the high pitch or low pitch tone, telling you that if you were close enough or not close enough. And from there, this is that air tone. So then what we kind of decided to do is kind of transition it into a phone app that you could access on your phone. There's many benefits to this, as it's just, a phone is much easier to have because most of us already have smartphones already, and that the size is much smaller. As you saw that it was a big cylinder. And then also that a phone has much more data, or you can store much more data, so we can actually record a lot more data points, so you can get a real-time reading instead of averaging 4 different numbers across however long you hold it for. So our costs and budgets right now, initially, phones obviously will be a cost, but we all have previous Samsung phones that have Android to us, so that's why that cost to us is free, because we already had previous phones. And the software that we used to code the data, we found online, and that was free also. So, and the only cost that we see coming into us is if we were to actually license this app, and that initial fee is $25.
For the progress that we've made so far, over there, the completed part, this is what we've done with the coding so far, and as you go down, it goes down in chronological order. So all of this was mostly done in this quarter, the accelerometer axis. We created a basic app that is actually able to turn on the accelerometer and read the data, and then print it out on the screen. And then a week or two later, we actually access audio files to that. So just like a music player, but we actually figure out how it works, how we go access the address and set the data source to actually play. And then around week 5, we were able to distort sounds. So we created an app where it creates a sine wave, and then we can adjust the frequency with the slider, and then it would distort tones in real time. So increasing the frequency, it produces a higher pitch, and if you move the slider down, it would produce lower pitch sounds. And just last week, we kind of combined all this, and we were able to produce an app where it takes the acceleration data and then takes the acceleration, only the x for right now, for simplicity, and we compared it, we plugged it into a linear function that was able to say that, for example, for higher positive accelerations, it would increase the frequency, and for negative accelerations, it would decrease. And we also set a cap to it, so it's to get better resolution as well. And also that if you're too far below, it's ridiculously low, and if it's way too high up, it's way too fast. And for recognition patterns, Hans going to talk about that.
Okay, so I was going to say earlier, so this blue here that you see is kind of theoretical, so that's our baseline that we'll be using. We're just right now using a sine wave just because it's easy motion. Like if you think about it, in only the x-axis, the sine motion, you'd be moving it just back and forth. So just do it as Kevin said, simplicity. That's kind of what we're kind of working on right now. And then this red curve is actual data that we recorded through the accelerometer in the phone. Why you can see the range between 1 and -1 is because what we did is we took the max value recorded and we divided all the accelerations by that max acceleration. So you can see that, and then we'll be able to get a range because nothing's going to be higher than that max value. And then from there, what we want to be able to do is measure the peak amplitudes between those two. As you can see, the peak amplitude is kind of when we first started, which is similarly bad. But as it goes on, we'll have a window, and then from here, the next peak amplitude we'll be finding is about here, and then you can see that the difference, that it's not being close, so that's when we'll be able to have it play a slower frequency of the song that we have.
So the feature that we're going to continue to work on is the debugging process, especially. Right now we're having trouble with how to actually control the threads and their life cycles. So, for example, when you run it, you create a thread, but then in order to, if you re-record a song, or if you play another song, it actually creates another thread, but since it's already existing right now, it creates an error and actually crashes it. And also, for code refinement as well, we need to actually improve, how heavy the memory, how memory heavy these functions are. And also, right now, it's hard to distort the music while playing actual audio files. Right now, we're only able to record songs, or maybe a good portion of it, and then we're able to, press it, play it. And also, we still need to figure out, or not figure out, but we need to implement how to filter out gravity. So, for example, we'll show you later, but then if you have the phone staying still in the Z component, actually there's still acceleration on it. And future tests, the smaller ones that we're going to continue on, is actually making it more pretty for the user, making better user interface. And also maybe if we have the time, we can actually control the pitch only, not the tempo, so doesn't sound like. I'll show you later. And we might implement an exploratory function, which Mel's going to talk about.
Yeah, so right now what we've been focusing on is a task-oriented mode. It's a therapist-defined motion, and the patient essentially, their goal is to do whatever the therapist does to the best they can. And within a certain percent error, as you saw in the graph, if they do it, say, within 90% of accuracy, the song will play correctly. One other benefit of using the app is that we can implement different modes into this to make the experience more interactive for the patient. So by adding an exploratory mode, we will basically define a random set of accelerations, and the patient essentially has to play around with the phone, and depending on how the song is getting distorted, they'll play around with the phone to determine what that set of accelerations was. And we can increase the levels of difficulty as they progress through each level. So the idea is that this allows for them to be creative with the app, and we can allow them to practice different ranges of motion, which ultimately goes back to our main goal, is to increase their overall range of motion with time.
Or just basic on the side, for communication-wise, we used Google Drive to share documentation and also keep track of meetings and such, and GroupMe, in order to coordinate meetings and such, and also GitHub, which is basically something that makes it easy for us to share code, and also the different revisions of the code that we have, and also the test apps that we made. And this is just a basic, very simple looking layout of what the app looks like right now. So over here we have the sampling frequency, which is the rate at which it samples the data. We start that by pressing record, and then once we're done, we stop recording. And then we can start playback, which creates a thread, but right now we can only do it one time. We have to restart the app in order to do it again. Now this part right here, this part was something that we created as an intermediate step in order to actually control it with motion. So in this step, if you click this, it produces a fly down menu where it has a bunch of other frequencies, and you can select it and then press it, and it'll change. So maybe, for example, 4,000, 8,000, 44 kilohertz, something like that. If you switch it while the song is playing to a different sample frequency, you press it with slow down or high pitch, low pitch, and you can keep on switching while the song is still playing. Now over here, this is the part where we actually turn on the accelerometer, we register a listener, and we're able to register, and then it leads us back to a callback method. we're able to go get the acceleration data and put it into the linear function and produce a frequency which is then played. And this one turns it on while this one turns it off, and we need to turn it off in order to save battery. And we're gonna go back. We have it, but then, like we said, we have to actually play it. We have to record it first. So if you just give us like 20 seconds. Oh, I mean, you don't have to shake it. So.
Take your time. I want to see this.
Oh, I hope it works. We tried it, but then. Pressure. Huh? I'm good. So right now we took a 20-second audio file and we sampled it at the exact same right here. And hopefully, we checked it like a few times, but you know, if it messes up, hopefully it doesn't. So right now, if you play back, it should play normally right now. And if you turn on the accelerometer, so hopefully with that we're able to actually, we're going to actually have a set of audio or have a set of acceleration beforehand, and let the therapist will move. And then with XYZ, and after we're able to filter our gravity, we'll try to match it, and then based on that difference, we'll hopefully distort it appropriately. And also we're thinking about distorting maybe other things instead of frequency, maybe like pitch or maybe haptic feedback as well, vibrations and such.
So some really cool things about this project that make this a very useful and interesting project to us. It gives occupational therapists a quantitative way to measure their patient's progress. Rather than just kind of guessing how much they can push their patient, they have a way of measuring what their current range of motion is, and then after they play around with the app, they can maybe increase that range of motion even by a degree or two. But a degree or two each time is progress, no less. And it's a more enjoyable and rewarding form of therapy for the patient. Another thing that we're going to work on later is putting whatever songs that the patient wants on there. So not just something that we put on there. So it's something that they want to listen to and that they want to move around to. So that's something that we are looking forward to with this project. And that's the conclusion of our presentation. Thank you.